I'll do, hopefully the proof is clear. I'll do just a couple of more examples. You take S5. Okay, so let's use this inefficient but clear description of an element. Let's say sigma is 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 1. So what is a cycle decomposition? So this is called cycle decomposition. So as I said, start with 1. See where it goes. It goes to 2. 2 goes to 3. 3 goes to 4. 4 goes to 5. 5 goes to 1. So sigma is a 5 cycle, right? So that's all. Because you have exhausted all the indices, there is no further cycle. In general, you will have a product of several cycles. In this example, sigma was an element of S9. It is a product of 3 disjoint cycles. See, when I say product, I mean I have told you how to apply product of cycles earlier. In this case, you start with 7 and see where it goes. It goes to 8. Because this is disjoint thing, 8 will not appear again. So 7 goes to 8, 8 goes to 7. 5 goes to 6, 6 goes to 5. 4 goes to 1, 1 goes to 3, 3 goes to 2. And 9 is not represented here because 9 goes to 9 itself. So in this example, sigma is a 5 cycle. One more example. So let's take in S5 again, let's take tau to be 1 goes to 1, 2 goes to 2, 3 goes to 4, 4 goes to 3 and 5 goes to 5. Okay, so what is the cycle decomposition of tau? So this is called tau. Tau is this. So you start with 1. 1 goes to 1, so you have, that is just a 1 cycle. 2 goes to 2, again it's a 1 cycle. 3, now you start with 3, which is the index not covered yet. 3 goes to 4 and 4 goes to 3. So you close the bracket and finally 5 goes to 5. So this is tau. But remember our convention, we don't write, because 1 cycle is unnecessary to write. There is no information that you gain by writing 1, 2 and 5. So see, tau is just a 2 cycle. Okay, so in this case tau is a 2 cycle. So now the general proposition is every element can be written like this. Every element has a decomposition as a product of disjoint cycles. Another property of this of disjoint cycles which is also clear. Another property of disjoint cycles is that if sigma and tau are disjoint cycles, then sigma tau equals tau sigma, that is, in words, sigma and tau commute with each other. See, remember that in general symmetric group is not abelian. S3 we have seen in example, a detailed description of S3 earlier, and we know that S3 is not commutative. So they in general 2 elements of S3 do not commute with each other. For example, so recall, in fact Sn is not abelian if n is greater than or equal to 3. Okay, so this is an exercise. In fact, S3 and S4, S5, they are not abelian. They cannot be abelian. S1 and S2 are obviously abelian because S1 is just a group with 1 element, S2 is a group with 2 elements. Any group of order 5 or less we saw is abelian. So those are abelian. And in fact, without that exercise, it's clear that a group of 1 and orders in that exercise also, it was very easy to conclude that group of order 1 or 2 is abelian. But Sn is not abelian. For example, if you take 1, 2 and 1, 2, 3, right? What is this? If this is sigma and this is tau. So remember, how do we multiply? We start on the right side cycle. So 1 goes to 2, 2 goes to 1. So 1 goes to 1 in this product. 2 goes to 3, 2 goes to 3 and 3 goes to 3 under that. So 2 goes to 3, 3 goes to 1 and 1 goes to 2. So we close the bracket, and again we don't write one cycle, so this is 2, 3. On the other hand, what is tau sigma? 1, 2, 3, 1, 2. So in this case, 1 goes to 2 and 2 goes to 3. So 1 goes to 3 and 3 goes to 3 in this, but 3 goes to 1 in this. So you stop there. 2 goes to 1, 1 goes to 2. So again we don't write the one cycle 2 consisting of 2. So we have 2, 3 and 1, 3. These are different. These are different. So 1, 2 times 1, 2, 3 is not same as 1, 2, 3 times 1, 2. So in general, Sn is not abelian. However, what did I say here? If they are disjoint cycles, then they commute with each other. In this case, they are not disjoint cycles, right? 1, 2 and 1, 2, 3 are not disjoint, because the index 1 appears in both, the index 2 appears in both, so they are not disjoint cycles. However, if they have the same, if they do not have any common indices, we must have that they commute with each other. So now let me prove that if sigma and tau are disjoint cycles, so however, so in general they don't commute with each other, but if they are disjoint cycles, then sigma tau is tau sigma. So why is this? If you think about it, it's clear, because when you try to write the product, what do? We first look at indices that are in sigma, right, and you see where it goes. But any index in, we first see indices in tau and see where it goes. Wherever it goes, it won't appear in sigma again, unlike in this example. In this case 1 goes to 2, but 2 goes to 1, because 2 appears here. But if there is no index that is common to both sigma and tau, whatever happens in sigma stays within sigma. So when we consider the product sigma tau, we look at indices in tau first, right? Because they are not present in sigma, right? Because they are disjoint cycles. This is very important. Because they are not present in sigma, it does not matter whether we consider their images, we consider them first or after sigma. Okay, so this is just something that hopefully is very clear. I am trying to write it. It may not be necessary, but let's just illustrate this. For example, if you have 1, 2 and 3, 4, this is sigma and this is tau. If you have 1, 2 and 3, 4, what I am trying to indicate here is 3 go, so look at the indices in tau. 3 is the first index, 3 goes to 4, right? But 4 is not present in 1, 2. So 3 goes to 4 under the product also. Similarly, 4 goes to 3 under tau, and 3 is not present in this. So 4 goes to 3. Similarly, 1 goes to 2 under sigma, and it's not affected by what happens in tau. So 1 goes to 2, 2 goes to 1. So we might as well write this as, which is tau sigma. Okay, so if the indices are disjoint, they are unrelated, they don't interfere with each other. So we have no problem, and we can just multiply them in any order. So the cycle decomposition, this means in the cycle decomposition of a sigma, I have already told you that every element has a cycle decomposition. Now I am telling you that in the cycle decomposition of an element sigma, the cycles can appear in any order, right? In the example above, in Sn, remember Sn, we discovered that it is 1 3 2 4 times 5 6 times 7 8, but now I am saying that there is no problem if we write it like this: 5 6 1 3 2 4 7 8, or 7 8 5 6 1 3 2 4 7 8 1 3 2 4 5 6, right? They are all same. That is because the indices are different, are disjoint. So whatever happens within 1 3 2 4 doesn't interfere with what happens with 5 6 and with what happens in 7 8. So I can do in any order. Okay. So the two important properties of cycle decomposition that we have learned so far is every element of Sn has a cycle decomposition, and the order in which cycle decomposition we write elements is irrelevant. So order in which we write is not important. We can write it in any order. So some other properties of cycle decomposition. So consider a k cycle in Sn. Let sigma be a k cycle in Sn. So we can write sigma as, remember, sigma can be written as I1, I2, Ik. So I must stress here that not every element is a k cycle by itself. For example, this element of S9 is not a cycle, it's a product of 3 cycles. So a cycle is just one cycle, so its cycle decomposition is itself. Those are very special elements in Sn. Sigma is a k cycle, means it's a single cycle, but in general elements of Sn can be products of more than one cycles. In this example, sigma is a product of 3 disjoint cycles. Now I am considering a single k cycle. I want to prove the proposition that the order of sigma in other words, the order of a k cycle is k. So order of a k cycle is k. So recall what is the order of an element. In general, order of sigma would be, by definition, the smallest positive integer d such that sigma power d is identity element. So we want to show that sigma power k is identity and sigma power any smaller thing is not identity. So in order to do that, let's find out what are the powers of sigma. So sigma is I1, I2 up to Ik, and recall what the meaning of this is. It sends I1 to I2, I2 to I3, so on, finally Ik minus 1 to Ik. And what happens to an index that's not inside I1 through Ik? Nothing happens. It is fixed by sigma. If a j is different from I1, I2, Ik, it sends j to j. So we don't need to worry about it. J goes to j for any j that's different from I1 through Ik. So now what happens to sigma squared? What is sigma squared? Remember, sigma squared, because the operation in the symmetric group is a composition, is sigma composed with sigma. Where does I1 go under this? So I1 goes to I1 under I2 under sigma, under another sigma it goes to I3. So I1 goes to I3 under sigma squared. So I want to keep track of the cycle of I1 under sigma. So I1 goes to I3. So I write it like this: I1 comma I3. I1 next to it is I3. What happens to I3? Let's figure out what happens to I3. Under sigma, I3 goes to I4, right? And what happens to I4 under sigma? It goes to I5. So I3 goes to I5. Similarly, I5 goes to I6, then I7. So I5 goes to I6 under sigma, and under another application of sigma, I6 goes to I7. So I5 goes to I7. So it keeps on going like this. Which element goes to I1? So of course here I should write Ik goes to I1 under sigma. Ik minus 1 goes to Ik under sigma. Ik goes to I1 under sigma. So you have Ik minus 1 here. Ik minus 1 goes to I1. What happens to Ik? It must appear in the previous place, somewhere in the middle. So what we have concluded is sigma squared is another K cycle. Remember, sigma squared is an element of the symmetric group, so it has a cycle decomposition. In fact, it is a K cycle itself, because where is Ik appearing here? See, Ik minus 2 goes to Ik minus 1 under sigma, under again sigma it will go to Ik. So Ik will appear here. Okay. So every element I2 will also appear, because I2 will go on. Where does I2 go? Ik goes to I1 and I1 goes to I2. So Ik goes to I2. So they all appear here. For example, if I take sigma to be 1, 2, 5, 7, let's say inside S7. What is sigma squared? Sigma squared is, I start with 1, I just skip one step. So 1, 2, then 5. So it's 1, 5. 5 goes to 7 under sigma, so and 7 goes to 1. So this is 1, 2, 5, 7. So 1 goes to 2, 2 goes to 5, and 5 goes to 7, and 7 goes to 1. So 5 actually goes to 1. 2 goes to 5, and 5 goes to 7. So 2 goes to 7. 7 goes to 1, and 1 goes to 2. So actually, as you can see in this example, what I wrote here is just wrong. So sigma squared is not in general a K cycle, as this example shows. Sigma is so I should not have written that. So sigma squared is not in general a K cycle, because maybe not all indices are covered there, as this example shows. So sigma is a 4 cycle, but sigma squared is a product of two cycles, right? Sigma is 1257, sigma squared is 1527, but doesn't matter. So sigma squared sends, in any case, sigma squared sends I1 to I3. What happens to sigma cubed? Sigma. So I am going to keep track of what happens to I1 under each successive power of I1, power of sigma. Sigma sends I1 to I2, right? This is the first step. Sigma squared sends I1 to I3. Sigma cubed sends I1 to I4. Remember, the fact that we are saying sigma is a K cycle implicitly means that if it's a K cycle, it means that I1, I2, Ik are distinct indices. Distinct indices, right? Otherwise there will not be K of them, so I won't call it a K cycle. And more than that, in a cycle we are not allowed to repeat elements, right? This is not a cycle, because if 2 goes to 2, but 2 also goes to 1 under this, so in a cycle we cannot have a repetition of an index. So if it's a K cycle, they are all distinct indices. So now let's come back to this. So sigma sends I1 to I1. Sigma sends I1 to I2. Sigma squared sends I2 to I1 to I3. Sigma cubed sends I1 to I4. And you can see that sigma k minus 1 sends I1 to 3 goes to 4, 2 goes to 3, so this goes to Ik. And this is not surprising, right? So after repeat k minus 1 times you apply this, I1 will go to the last index. So since I2, I3 up to Ik are all distinct from I1, remember that is the point of being a k cycle. This is not I1, this is not I1, this is not I1, this is not I1, right? They are all distinct because I1, I2, I3, Ik is a k cycle, and sigma can't be identity because sigma sends I1 to I2, which is different from I1. So sigma cannot be identity. I don't care about what it does to other elements. It sends I1 to I2. So identity element is supposed to send I1 to I1, right? But sigma sends I1 to I2, so sigma can't be E. Sigma squared sends I1 to I3, so it can't also be E, right? Because I3 is different from I1 and an identity element sends I1 to I1. Similarly, sigma cubed can't be E, and finally sigma k minus 1 can't be E. So sigma is not E, sigma squared is not E, sigma cubed is not E, sigma k minus 1 is not E. So order of k of order of sigma has to be at least k, right? Remember, order of sigma is the least positive integer d such that sigma power d is identity. So here sigma is not identity, sigma squared is not identity, sigma k minus 1 is not identity. So order has to be at least k. Is it k? Let's find out what sigma k does. Under sigma k, I1 goes to I1, right? Because under sigma k minus 1, I1 goes to Ik. If you apply sigma again, it goes to I1. So far so good. Sigma k has the chance to be identity element because I1 goes to I1. What about sigma k I2, right? So I2, remember, under sigma goes to I3, under again sigma it goes to I4, and if you keep applying this, at some point you will get Ik, then I1, then I2, right? So if you do k times, okay, so sigma k of I2 is also I2 because the same, it's a cycle, right? And as I said, cycle can start with any of the indices in it. So I said here with I1, but I1, I2, Ik can be written as I2, I3, Ik minus 1, Ik, I1, right? And so now I2 is the first one. In the previous calculation we said the first one after k times will reach the first one again. So I2 after applying k times we get to I2 again. So similarly sigma k power I, any of them, so sigma power is I3, sigma k power I4 is I4, and so on. Finally sigma k power Ik is Ik. So we have sigma k is the identity element, right? Because sigma k sends I1 to I1, I2 to I2, I3 to I3, Ik to Ik, but does it send other indices that are not inside I1 through Ik to themselves? Of course it does, because sigma itself sends any index that's not equal to I1, I2, Ik to itself. So if j is not in I1 up to Ik, sigma of j is j. So sigma k of course will also send j to j. So in other words, sigma k sends any index to itself. So sigma k is identity and sigma any smaller power cannot be identity. So this proves the proposition. So this proves the proposition. So sigma, which is a k cycle, has order k. Okay, so an order of a k cycle is k. So for example, the order of 1, 2, 3, 5 is 4, right? Because it's a 4 cycle. And it's a good exercise for you to check that. In fact, it is 4 by multiplying it out. So maybe I'll just do quickly. 1, 2, 3, 5 squared is 1, 3, 3 goes to 1. So that's 1, 3, and 2 goes to 3, 3 goes to 5. So 2, 5. Okay, what is 1, 2, 3, 5 cubed? So 1 goes to 5, and 5 goes to 2, and 2 goes to, sorry, so 1 goes to 5, 5 goes to 3 actually, and 3 goes to 2, and 1, 2, 3, 5 to the 4th is identity. Okay, so this I'll let you check. So check this. And of course, the point of the previous proposition is that you don't have to do this calculation every time. Okay, 1, 2, 3, 5, you can immediately say, because it's a 4 cycle, it has order 4.